So now that we know what an antiderivative is and we have the notation to talk about it, we're just going to do some practice problems. All right, so before we do the practice, we have the power rule for derivatives, that if I took the derivative of x to the n, I get n x to the n minus 1. While I'm undoing this, instead of subtracting, I'm going to add in the exponent. And instead of multiplying down, I'm going to divide. So I'm basically just doing the opposite of the power rule because I'm going backwards from this process. All right, so if we're doing a problem like this, all right, the integral, the antiderivative of this whole polynomial, again, I can just think about it as 4 mini problems, because I can break it up over the addition and subtraction. All right, so my answer, well, I have an x cubed, so I'm going to add 1 to that power and divide by the new power. Right. Add 1 to x squared, become x cubed, divide by that. Add 1 to x to the first to become x to the second, divide by the new power. All right, here, if there's a constant, right, it's technically our variable raised to the 0 power. So if I add 1 divided by the new one, I'm going to get 4x. And that makes sense because if I take the derivative of 4x, I get 4. And I always have my constant that I don't know exists. All right, so if you were to take the derivative of what we just wrote, all the new powers and those denominators are going to cancel, and I'd get back to what I had in my integral. All right, so when you're using the power rule, you add 1 to the exponent and divide by the new power, not the old power. All right, then we start introducing other things into integrals. And a lot of times you're going to do some simplifying first before you do the integral, because it's not as obvious exactly what I should take the derivative of to get this function with a fraction bar. All right, we know when we have fraction bars with derivatives, that's not great because you have to do the quotient rule. All right, so maybe there's ways we can get rid of the fraction bar. In this case, there is, because I can rewrite this integral like this. Most of the times when we're adding fractions, we combine 2 fractions into 1 using a common denominator. If we can do it backwards, I can split up this 1 fraction into these 2 separate fractions. And that allows me to simplify using my exponent rules. X squared over x is x. I remember the cube root of x, I can rewrite using an exponent as the 1/3. So that 4 is going to stay there. I have x to the 1/3 on top and x to the on the bottom. All right, if I use my exponent rules, it's going to be x to the negative 2/3. I take the 1/3 power, subtract the 1 power on the bottom. All right, there's an x there that I forgot to write. And now I just rewrote it using powers, so I can do the opposite of the power rule we did. All right, add 1 to the exponent, divide by the new power. I add 1 to the exponent, so I'm going to add 1 to negative 2/3, give me 1/3. I'm going to divide by that new exponent and add c. And the only thing, just to kind of simplify a bit at the end, 4 divided by 1/3 is going to be 12. All right, so when you see a problem with only just x's and power of x's, even if there's a fraction, you can still do some simplifying. I make the problem simpler by combining things, all right, and then taking the antiderivative after that. All right, so make sure when you're thinking and you see the symbol for antiderivatives, just make sure you think about some simplifying stuff before you do that, because it's going to be a lot simpler if you simplify first before doing the integrals. All right, same thing here, tangent of x times cosine of x. All right, it's not obvious when I'm going backwards, undoing the differentiation process, what this antiderivative would be. But if I go out and try to do some simplifying first, all right, well, tangent is sine over cosine. And this happens a lot with our trig functions. I rewrite our trig functions using sine and cosine, and then you can see these cosines cancel. So now we're just taking the antiderivative of sine of x, which is going to be negative cosine of x. Again, plus c, because we don't know that constant that would have been there. All right, also be careful with the antiderivatives. We're going backwards on our sine and cosine wheel. So if I started at a positive sign, all right, my antiderivative is going to be negative cosine, okay? Because when I retake the derivative, I'd get negative negative sign would get me back to that positive sign. All right, so just be careful with negatives when you're dealing with sine and cosine and antiderivatives. And one final example for the videos, the integral of 1 over the square root of 1 minus x squared. This one looks really complicated. You can't really separate it out into different fractions like we did before because there's no extra terms. You could try to multiply by conjugates and things. But if you look at our derivatives that we had at the start of the semester, or in the last semester, we took the derivative of sine inverse of x, and we got exactly this. So it turns out this is just sine inverse of x plus c. So we're going to have to go back and kind of look at our old derivatives that we learned, specifically these inverse trig functions, because it's not obvious that this is related to that at all. But we did some work in the first semester kind of explain why this is the derivative of sine inverse of x. So now we're going backwards. It's also the antiderivative of that expression. All right, here's one for you to try on your own. Again, you're going to want to break it up into smaller pieces and just make sure you can take the antiderivative of this expression.